And we can also find where that line hits any of the axes, right? I mean, I could have done YZ plane, could have done XY plane, could have done XZ. I could have done any plane, right? Could I have done, not any plane, sorry, take that back. I could have said, like, where does it hit the plane Z equals 3? Z equals 3 would mean 1, 2, 3, like this right here. We would just need the Z to be 3, right? So you would just set that Z equal to 3, solve for T, plug that T back in and get everything. Okay, we good? Yes?
Just theoretical question out there.
Yeah.
If a vector was somehow parallel to that plane, I would be able to figure that out. So like if you had if the question was like, when does it intersect that plane? But by some miracle, it's like
Great. Yeah, that's a great question. So,
is there anything to identify the fact that it's parallel?
yes. So let's take a simple example, like something that would be very easy for us to see. All right. Let's say that the vector equation of our line. Let's say the vector equation of our line was the x-axis. Okay. So what would that vector equation look like? The vector equation of the line that creates the x-axis. So start with your point. What's your point? Origin. Okay, so it's going to be 0, 0, 0 is going to be our starting point. This is our R naught, right? That's our R naught. Plus T times. Now you need your direction vector. What would be the direction vector down the x-axis? 1, 0, 0, or I hat, right? 1, 0, 0. So you'd have 1, 0, 0. Now, if I put this together, right, if I put all this stuff together, this is the vector equation I get, T, 0, 0, okay? Now, where does this line intersect Z equals 4, right? This plane up here. Well, they don't, right? But how would we know that? Well, I would need the Z to be 4, and it's always 0, so it wouldn't be, right? Now that's a simple example because I kept everything nice. If you tilt it, you would have something similar happen as well, where you would get something that you can't solve. Yeah.
Okay.
All right, we ready to move on? Given 2 points, we can find the vector equation of the line through those. Every example I've given you so far, or the only example I've given you, I'm working in 3-dimensional space. I'm assuming that if we went to 2, it would be even easier, right? Because we only have 2 components to worry about. Here we go. Determine that these lines are skew. That is, that they do not intersect and they are not parallel or orthogonal. So I've given you 2 lines. I'm calling it L1 and L2. Now look at my definition of L1. Do y'all see that this is the vector equation of a line? Do y'all see that that's the vector equation of a line? Just like we did a second ago? Can somebody real quickly tell me a point on this line? 1, negative 2, 4. Good. Can y'all tell me, y'all getting that by just doing this, right? Boom, boom, boom. Sorry. Those 3 numbers, right? All right, can you tell me the direction vector of this line? Direction vector of this line. Nope, not the T. It's the coefficient only. 1, 3, negative 1, right? You all following? Now, this one, I'm using S instead of T because I don't want us to confuse the 2 variables. The T is going to draw me all the vectors on this line. The S is going to draw me all the vectors on this one. Can somebody give me a point? Can you all give me the 1 point, just any point on this line, the easiest one? 0, 3, negative 3. And the direction vector of this line? 2, 1, 4. Yes? Okay, let me kind of recap a little bit of what we just did. So for this L1, we have 1, negative 2, 4 is a point. That's just fun, just so we know, is a point on the line. Might be useless information, but it's just something we can recognize that that is a point on the line. More importantly, the vector 1, 3, negative 1 is the direction vector, right? of that line. For the second one, L2, we have the point 0, 3, negative 3 is a point. I'm just going to put a point. But more importantly, the vector 2, 1, 4, right, is the direction vector. I'm just going to put dir vector, is that all right? So this is the direction vector of that line. This is the direction vector of that line. Y'all agree with that information? Okay, we are to show that these lines are skew. That means we have to show that they don't hit each other, they don't intersect each other, they don't cross through each other, they're not parallel, and they're not perpendicular, orthogonal, right? So let's start with the easiest one. What do you think is the easiest of those three things that we have to show? That they don't hit, that they're not parallel, and they're not orthogonal. Which of those three do you think is the easiest to show? Orthogonal. That they're not orthogonal. Because if they were orthogonal, what would that mean? The dot product of what? Of the direction vectors, right? So whatever this line is has a direction. Whatever this line is has a direction. If they were orthogonal to one another, right, then when I dot product those two vectors, I should get 0. So I'm going to first show that they're not orthogonal. Showing L1 and L2 are not orthogonal. Can you push that trash can up against the back? You see that? That was going. Oh man, I'm gonna act like I didn't see that. Okay. Yeah.
Basketball was not good.
All right, I'm about to show this. So I'm showing that L1 and L2 are not orthogonal by taking the dot product of the two direction vectors, right? So let's label these. How about we label this V1, okay? Because in the definition for the line, we called V the direction vector. So I'm going to call V1 for it's the direction vector of the first line. And this one I'm going to call V2, direction vector, right? So dot product, right? Okay, so now we're checking what's V1 dot V2. So I'm taking V1, which is 1, 3, negative 1, dotting it with, oh, that's terrible. Dotting it with the other one, 2, 1, 4, and we're getting, what does that come out to be? So we're doing 2 times 1, 2, plus 3 times 1, 3, plus negative 1 times 4 is negative 4, and our answer there is 1, right? And 1 is not 0, right? If it was 0, then the dot product being 0 would give us orthogonal, right? So they're not orthogonal. How about parallel? How do you check to see if they're parallel? You can look at the magnitude of the cross product, can't you? You could. There's an easier way. For two lines to be parallel, what does it mean? Or for two vectors to be parallel, they have to be what? Scalar multiples of one another, right? So do you think it would be easy for me to show you that these are not scalar multiples?
Yeah.
How? How do you show it though?
You just make one value equal to another and see if they're the same equation.
Yeah, so like in order for these to be scalar multiples, this 1 has to become a 2, right? Which means I have to multiply by 2. But if I multiply that by 2, it becomes 6, and that's not a 6. See, there's no way to get all three of these components to turn into these three with one number being scaled through all of them. So that's a little harder to actually write down, but I'm just gonna try at least, right? Let me move that up. I don't think I need that. So that's showing that they are not orthogonal. Okay. I'm also going to put here, I'm going to try and show that L1 and L2 are not parallel. And to do that, I'm going to show that 1 if I take some constant c and I multiply it times the vector 1, 3, 1, you are never going to get the vector 2, 1, 4, right? Like it's not possible to make that happen. They're not scalar multiples of another, of one another. There's no way to do it because you would have to have what? You would have to have 1 times C1 would have to be 2, but at the same time you need 3 times C to be 1, and then you'd also need negative 1 times C to be 4. Do you see what I'm saying? Like you need this times that to be that, this times that to be that, this times that to be that, but that means C is going to take on 3 different values, right? No, it's not happening, right? All right, so we've shown that they're not orthogonal, shown that they're not parallel. You all happy with that or understand that? Any questions on that? Showing they don't intersect is the hard one. So how do you show that they don't intersect? Well, what if they did? Maybe you think about it that way. If they did intersect, right? If they did intersect somewhere, right? 2 lines. If they did hit each other, then there's some point common to both, right? Where they both have the same x coordinate, y coordinate, and z coordinate at the same point in space, right? Which means I should do what? Set them equal. So I'm asking myself, is there a t that I could plug in here and an s that I could plug in here to make these the same? Can I plug that same t into here and that same s into here and get these two to match? And can I plug that same t into this and that same s into this and see if those match? So can I find a t and an s that make the components equal to each other simultaneously? Make sense? So I'm going to put here, do they intersect? So intersect, question mark, right? I don't know if they intersect yet. So do they intersect? I'm going to ask myself, can I find a t and s such that these 3 things are true? First, 1 plus t equals 2s. The next thing that has to be true is negative 2 plus 3t has to be 3 plus s. And the last thing that has to be true is 4 minus t must be equal to negative 3 plus 4s. See what I'm doing? Trying to figure out what number I can plug in that's going to make my x, y, and z all simultaneously the same. Which means I'm about to solve a what? What do we call that right there? System of equations. How many equations do we have? 3 equations. How many unknowns do you have? 2. Two unknowns, 3 equations. Is it possible to have a solution? Yes, it is possible. All right? So we're going to see if we do. So how would y'all like to solve this? I mean, there's all sorts of different ways. I mean, we could use matrices, or we could try like a substitution. What do y'all want? I don't really care.
I think you should just like add all together.
You could add the first one, the third one, and get rid of your t.
You could add, yeah, so you can add any 2 together at the same time. You could actually do 3 if you want, but let's just do 2 at a time to keep it simple. Well, I got to sneeze here. Okay, I heard add the first and third one together. Is that all right? You all okay with me doing that? Okay, we're going to take, let's just call this equation 1, equation 2, equation 3. So let's take equation 1 and add it to equation 2. 3. Are we allowed to do that? Why? Who says we can do that? You're trying to solve a system of equations, right? you can add any two equations together and get a new equation and replace one of those with that. Who says we can do that? The math gods, right? So this is referred to, what we're doing here is what's called Gaussian elimination. So Gauss is the mathematician who came up with this method and the proofs of why you can do all this stuff, Gaussian elimination. So all of the things you can do in matrices, right, where you're like add rows together, scale, all that, that's all Gaussian elimination, based on Gaussian elimination. So we are allowed to take two rows, add them together, and then look at that, or two equations, add them together and figure out what we get when that happens. So when we add the first and third, what do we get? T's cancel, you get 5 equals, I should say, 5 equals what? Negative 3 plus 6s. Right? That's what happens when I add the first two equations together. And then I can do that again, right? I can do that with like the first and the second one, or I can do that, or I can solve this for s. You want me to solve that for s? We can solve that for s. Okay, solve that for s. What do we get? 4/3. S is 4/3. So add 3 to both sides, you get 8 equals 6s, divide by 6, 4/3 reduce. Okay, so if these are ever going to all three be simultaneously true, this is the value of s that has to take on this value. And now what we do is we plug s into those and see what we get for t. So let's go back to equation 1. Let's replace. I get 1 plus t equals 2 times s, right? Like that. I've replaced s with 4/3. And that means that 1 plus t must equal 8/3, which means t must equal 5/3. Thank you. 5/3. So we're subtracting 1 on both sides. Subtract 3 over 3, we get 5/3. Okay, so it looks like I have a solution, right? It looks like when s is 4/3 and t is 5/3, we're in business. It has to be true for all. So what I need to do is I need to make sure that this is going to work. What equations have I been working with? The first and the third? This should work for the first and third, but it needs to also work for the second. So let's check the second now. Running out of room here. Let's check equation 2. And if I replace negative 2 plus 3 times, let's see, t was supposed to be 5/3. And then the other side, 3 plus s, but s is supposed to be 4/3. You'll see all I'm doing is replacing t and s with what I think it's supposed to be. You're going to basically find out that that's not true. These are not the same. They're not equal. And because they're not equal, that means that there's no solution. There's no s and no t that will solve these simultaneously, which means that they don't intersect one another. So these lines are skew. Not parallel, not orthogonal, and they don't hit each other. Okay? Can I move on? Or do you want me to clarify anything here? We're okay? All right. All right, now let's talk about planes. That was all lines, now let's talk about planes. So we're going to talk about the equation of a plane in three-dimensional space. And you probably are thinking, okay, well, we just talked about lines, which we've talked about in the past, and we found a vector equation for a line, right? So it seems natural to think, okay, well, next thing we should do is talk about planes and find the vector equation of a plane, right? It seem natural to you? It's not what we're going to do, all right? Vector equations of planes comes much later in this class. We're not quite ready for it here at this point. So we're going to go to just the generic standard equation of a plane the way you've probably seen it in the past. So what do we need to define? What do we need to define a line, right? Let's go back to what we need to define a line. You need a point on the line and a direction, right? A point and a direction. Or just 2 points on the line, right? That's for a line. What do we need for a plane? You need 3 points, right? If somebody gives you 3 distinct points, there's only one plane through those 3 distinct points. So that's the minimum condition we need, right? 3 points. Well, it turns out that in order to define a plane, yes, 3 points will work. They will work, 3 points, but sometimes we don't have all that information. Instead, all we do need are 2 things. First, we need a point on the plane. So I need a point. Just give me a point.
131.
Okay, yeah. Okay, yeah, that's right. So what would you say?
131.
131. Here we are. We're at 131. That point, if I tell you that point's on the plane, I don't need 2 other points. All I need now to define a unique plane going through this point is a direction vector of the normal vector to the plane. So let's just act like this was the plane. Okay, and then let me put that point on here. Let's just act like that's the point on that plane. If I give you a vector that's orthogonal to this plane, do you all agree that that vector right there uniquely defines this plane? If I change the direction of that vector, it changes the plane, doesn't it? So you only need 1 point and what we call the normal vector to the plane. Any vector perpendicular to the plane is all you need. So it's kind of like with a line, you need a point and a direction, right? For a line, a point and a direction. Point, direction, I've got the line. For a plane, you need a point and a vector, but that vector needs to be the normal vector. It needs to be running perpendicular to the plane. And then you've got it, you've defined the plane. So we have some notation for this, right? If somebody gives us a point, okay, x naught, y naught, z naught, well, then we can convert that, we could convert it to a vector, but we're going to leave it as a point. The normal vector that's pointing out of that plane, that normal vector, we are going to call it n, right, the vector n, and it's going to have the components a, b, c. That's the standard notation we use for the normal vector of the plane, the vector a, b, c. And it's any vector that is orthogonal to the flat sheet of paper. If we have those 2 pieces of information, then the equation of the plane, not the vector equation, the standard algebraic equation of the plane is written as follows. And I'm going to do an example, but I'll put that formula on the board on the side here so we have it. So if x naught, y naught, z naught is a point on the plane, and the vector n equals the vector a, b, c is any normal vector, and when I say normal, everyone understand what I mean? The normal vector to a plane is a vector that is what? Perpendicular to the plane, right? Okay. Any normal vector, then a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0 is the equation of the plane. In yellow here, all I'm saying is what I started with. Like, we're not going to talk about vector equations of planes yet. We're going to talk about that later. So if we take that equation here and we distribute the a through and the b through and the c through, distribute through, then we would get this. So this right here would be an expression with x in it. This would be with y. This would be with z. These would all be numbers. Think about it, because x naught, y naught, z naught is a point. So it's like the point 135 or whatever you give me. So if I distribute this number a, b, and c through the parentheses, this will have a variable in it, this will have a variable, this will have a variable. All of these are numbers. We could put all of those together as a number, and we call that usually d. And then if we do that, that equation kind of simplifies to be this. All right, let's do an example. Okay? Let's start simple. I'm not going to do that one that's there. I'm going to get to that one in a moment. Let's just start real simple with this. So I want us right now, I'm going to give this to you. Find the equation of the plane through this point, -3, 1, 7, with normal vector n equals 2, -1, 4. This is just to make sure you understand what's going on. So we want the equation of the plane through that point, and I gave you the normal vector. If you have the point and the normal vector, you're just going to plug right into this formula, right? There's no more work to do. So for us, what's A, what's B, what's C? What's A, B, C? Yep, this is A, this is B, this is C, right? And then this is our X naught, Y naught, Z naught, right? And then we just plug and chug right into the formula. So according to this, it'll be A, which was 2, parentheses, X minus X naught. So for us, because X naught's negative, it's going to be plus 3. And then we're going to have, let's see, plus B. What's B for us? -1, so I'm going to put minus, I don't need the 1, but I'll put it there. And then what goes in this parentheses? Y minus 1, right? Y minus 1. And then C, which is 4, so plus 4. And then Z minus 7, right? Equals 0. That is the equation of that plane that goes through that point and has this as a normal vector. And that's fine. That answer is perfect. We can leave it like that. But to show what the previous note was saying, let's go ahead and distribute this 2 through. These numbers through. Distribute, 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 and we will get 2x plus 6 minus y plus 1 plus 4z minus 28 equals 0. 2x minus y plus 4z, that's all the stuff with variables in it. And then we put all our constants together. And let's keep all our constants on the left side for now. What do we get there? Minus 21? Sounds good. Equals 0. That right there is the equation of that plane. Can you graph this in Desmos? Do you all know Desmos? Yeah. You all know Desmos, right? Yes? How many of you don't know Desmos? It's okay if you don't. Desmos? Most people use Desmos for graphing. Does Desmos graph three-dimensional? You don't know? Don't know, right? We use it to graph in 2D. Okay. As of right now, I don't believe Desmos does 3D. But there's another program, GeoGebra. Okay, I have a link here, GeoGebra. Okay, and I like Desmos more, but for 3D, GeoGebra is really kind of the only thing we've got. Well, I'm saying I use Wolfram Mathematica, the program I use to do the notes. I paid for that, right? I'm saying free, like you can access it from any website, right? This is the best thing that's out there that I can find. I haven't looked in a while, though, so maybe there's something else. So when you go to this GeoGebra, you go to graphing here, and you drop this down, you put 3D calculator, and now it gives you a three-dimensional. Okay, and look, they actually do red, green, blue, which is kind of crazy, because I don't know if they copied me. No, they didn't copy me. I'm not sure why kind of cool. All right, so now what I'm going to do is just over here, I'm just going to type in this equation. So 2x minus y plus 4z minus 21 equals 0. And there it is. There's the plane. You see it? And let me see. I also, didn't we have a point there? What was the point I gave you? Negative 3, 1, 7?
Yes.
So notice how I typed that in? I just did like parenthesis, right? Where is it? There it is. Okay, the point. There, see the point? See if that point lives on the plane? And I think, yeah, if you like kind of just start, if you start moving it and let it go, it'll just start, it'll go on its own, and like, that's kind of cool. Shit, I wish I had something like that when I was a student, right? Like the ability to just go graph something three-dimensionally.
How did they imagine this pre-technology?
Yeah, it's harder, right? Which, a little off topic, but in the same realm of things. So, how much do y'all know about this? How much do you know about the solutions to this equation? What are the solutions to that equation? Yeah, so you run into a problem here. I have to take square root of both sides, right? Plus or minus square root, negative 4. So now you need to bring imaginary numbers, right? So how much do you study imaginary numbers? Very little, right? You saw them in what, in college algebra? Have you seen them since? Pre-cal, they weren't there, right? Cal 1, Cal 2. We're not going to see them here either, right? And there's a reason. The reason why is because when it comes to imaginary numbers, and if you don't remember this, that's okay. I'm just kind of bringing this up. When we talk about real numbers, right? I'm going off on a tangent here, but we're going to do it. When we talk about a real number, we're talking about like a point on the number line, right? And then if we have a function, let's say we have the function f of x equals, let's do a linear function, 2x plus 1. What would this function do to that number 1? If I plug 1 into that function, what would it do? It would give us an output of what? 3? So it basically takes that number and drops it off over here at 3, doesn't it? That's a visualization of what that function does. What would it do if I plugged in the number, how about 2? Where does 2 go? 2 gets taken to 5, right? Imagine I try this for all the numbers over here. Wouldn't this look like a jumbled mess? Yes? So what we do instead is this. We say, look, we're going to draw one axis, R. This is going to be our input, the number we're plugging in. And then we're going to draw an axis perpendicular to that. That's another number line. And this is going to be our output. So that when I plug in 1, I got 3, right? I put a dot there. When I plug in 2, I get 5, right? I get a dot there. And all of those can be, doesn't go through the origin, but you get the idea, right? This is a visual representation of that function, right? It shows you the input and the output. The input is a real number.